In the last lecture, we were considering a problem of transport into a finite domain, unsteady transport into a finite domain in a cylindrical coordinate system. So, the equation of motion was the energy balance equation with constant thermal diffusivity in a cylindrical coordinate system. The configuration we were considering was you have a cylinder at time at temperature T is equal to T1. Okay. You have a cylinder at temperature T is equal to T1 and that is dipped into a fluid at temperature T is equal to T0, okay, at initial time. So, this hotter cylinder is dipped into this colder fluid and we would like to find out how the temperature field within the cylinder changes as time progresses, assuming that the temperature at the surface of the cylinder is equal to T0. Okay. So, the boundary condition is that at r is equal to capital R, which is the radius of the cylinder, T is equal to T naught, the temperature of the fluid. At time t equal to 0, the temperature is T1, the initial temperature of the cylinder for everywhere within the cylinder for r less than r. Okay. And we had to find out the temperature profile with these boundary and initial conditions. Okay. We had scaled the temperature as T minus T0 by T1 minus T0. So, that at r is equal to 1, the scale temperature is equal to 0. Radius is scaled by the cylinder radius, of course, and as t at t is equal to 0 for r less than 1, r star less than 1 within the cylinder, the temperature is the higher temperature T1, the initial uniform temperature of the cylinder. So, those were the boundary and initial conditions that we were going to use to solve this problem. The radius of the cylinder is scaled by the radial coordinate is scaled by the cylinder radius and time is scaled by the diffusion time over a length r. Okay. And in this particular case, in the limit as t goes to infinity, you would expect the temperature to be uniform everywhere, okay, because of the temperature at the surface is T0. You would expect the cylinder temperature everywhere to be T0 in the limit as time goes to infinity, so that there is no flux at steady state. Okay. And therefore, the steady temperature is just 0. Therefore, the transient temperature is the same as the total temperature when expressed in scaled form. Okay. So, I had shown you how to formulate boundary conditions. The original problem has only one boundary condition at r star is equal to 1, t star is equal to 0. Okay. The coordinate r star varies from 0 to 1. Okay. At r star is equal to 1, there is a physical boundary. At r star is equal to 0, there is no physical boundary. Okay. It is within the material. However, since this is a second order differential equation, we have to solve subject to conditions at two boundaries. And the condition at r star is equal to 1 follows from the symmetry requirement that as I approach the axis, since there is no physical boundary at the axis, as I approach the axis, the derivative of the temperature has to be uniquely specified independent of the direction from which you approach the axis. If the derivative is non-zero, as shown by the red lines on the figure on the left, the derivative will not be uniquely specified at that location and you will have a cusp in the temperature field at that location, and that is unphysical because there is no physical boundary there. So, you cannot have a temperature or the derivative of the temperature being discontinuous at that location. The only way that the derivative is uniquely specified at that location is if the derivative is equal to 0. And from that we got the boundary condition that r star is equal to 0, the temperature derivative has to be equal to 0. Okay. So, this condition emerges from symmetry even though there is no physical boundary at that particular location in r star is equal to 0. And at t star is equal to 0, the temperature was equal to 1 for all r star less than 0. We had formulated the separation of variables problem Okay. Write the temperature as the product of two functions. One is a function of r, the other is a function of T. Substitute into the conservation equation, divide throughout by f times g, and then you will get an equation in which the left side depends only upon time, the right side depends only upon r, and therefore, both the left and the right have to be constants. The constant has to be negative, so that the function g decreases exponentially as time progresses. If that constant is positive, the function g will increase exponentially and it will never reach a final steady state. It will reach the final steady state only if the function g decreases exponentially as time progresses, and therefore, that constant has to be negative. It has to be the same constant for the left and the right sides, only then are the two left and right sides equal, and therefore, the equation for r turns out to be of this form. Okay. How do we solve this? Okay. The way it is usually represented is to multiply it throughout by r square. Okay. So, I will get r square d square f by dr square plus r df by dr plus beta square r square f. This has to be equal to 0. Okay. And if you look at the first two terms on the left, they are both equidimensional in r. That is, you have an r square times the second derivative with respect to r. The second term is r times the first derivative. Okay. So, if I define a new radius, r star is equal to r plus is equal to beta times r star, the first two terms on the left will not change, okay, because the derivative with respect to r plus is 1 by beta times the derivative with respect to r star. Okay. So, the equation becomes r plus d square f by dr plus square plus r plus df by dr plus plus r plus square f has to be equal to 0. Okay. This is the equation, and we also have to recast the boundary conditions in terms of this variable. Okay. At r plus is equal to 0, the derivative has to be 0. Okay. Because r plus is equal to 0 is the same as r star equals 0, and the derivative with respect to r plus is 1 over beta times df by dr star. Okay. That is the derivative. Okay. Okay. That is the first boundary condition. The second boundary condition is that at r star equals 1, okay, when r star is equal to 1, r plus is equal to beta. Okay. At r star is equal to 1, r plus is equal to beta. Okay. At this point, f has to be equal to 0. Okay. F has to be equal to 0 at r plus is equal to beta. Okay. That is the second boundary condition for this function f when expressed in terms of r plus. Recall that when we had done the same solution in a Cartesian coordinate system, okay, when we had done the same solution in a Cartesian coordinate system, okay, we had recast the boundary conditions so that they are homogeneous at both boundaries. Okay. We had recast the boundary conditions by subtracting out the steady solution. By subtracting out the steady solution, we had recast the boundary conditions so that they are homogeneous in both spatial boundaries, and because of that we were able to use orthogonality relations for the solutions. In this particular case, the boundary conditions are homogeneous at both spatial boundaries already. The reason is because the steady solution is equal to 0. Okay. So, therefore, at r plus is equal to beta, I have one solution f is equal to 0. At the center, I have the derivative is equal to 0. Both of these are homogeneous boundary conditions. Okay. So, in this particular case, we by default the boundary conditions turned out to be homogeneous. Okay. So, therefore, we do not have to explicitly remove the steady solution. Okay, good. So, how do we solve this equation? Okay. This equation comes in a class of what are called equations called the Bessel equation. Okay. Okay. The Bessel equation in its original form is r square d square f by dr square plus r df by dr plus r square minus n square into f. Okay. So, this equation corresponds to the Bessel equation with n is equal to 0. Okay. If I take this Bessel equation and substitute n is equal to 0, I will get the equation for the heat conduction in the cylinder that I originally had. Okay. You recall that we had got a similar equation for transport in a Cartesian coordinate system, except that this middle term was not there. Okay. This middle term was not there. Other than that, the equation was the same, and the solutions were sine and cosine functions. Okay. In that particular case, okay, the solutions were sine and cosine functions. The solution in this case are what are called Bessel functions. Okay. F is equal to a, okay, times j n of r plus b times y n of r. These are the solutions for a general value of n. Okay. These are the solutions for a general value of n, and the solution for this equation is when n is equal to 0. Okay. That is, the f is equal to, let me take this down. Okay. F is equal to a times j 0 of beta r plus b times y 0 of beta r. Okay. So, that is the solution for n is equal to 0. Okay. These functions j 0 and y 0 are can be calculated numerically, and they have been tabulated in standard tables. So, you can refer to them to find out what are these Bessel functions and their values at specific values of r in a manner similar to the sine and cosine functions. Okay. In contrast to the sine and cosine functions, the amplitudes are not a constant, that is, the maximum and minimum is not a constant, it is not equal to 1, and the spacing between zeros is also not equal to not regular. Okay. So, if I plot, okay, x versus j j0 of x and y0 of x. Okay. So, let me color code it. the function j0 is actually equal to 1, okay. It is equal to 1 at x is equal to 0, okay. And if I plot for example 2, 4, 6, 8 etc., this decreases and then it has an oscillatory shape, okay. It has an oscillatory shape. Okay. And the amplitude decreases as x increases. Okay. So, the amplitude actually decreases as x increases. Okay. The amplitude decreases as x increases and it goes on oscillating. You have an infinite number of places at which it crosses 0. The amplitude decreases as x increases and the spacing between zeros increases as x increases. Okay. y0 actually diverges logarithmically as x goes to 0. Okay. It starts at minus infinity, it has a logarithmic divergence and then it also oscillates. Okay. And its amplitude also decreases as x increases. Okay. And each of these passes through 0 at discrete locations. Each of these passes through 0 at discrete locations. Okay. So, for example, for j0 it passes through 0 at discrete locations. The first few locations are here, it is the first one is 2.405, the second one is 5.52, the third one is 8.65, etc. The next two are 11.79 and 14.93. Okay. So, it passes through 0 at discrete locations. Okay. Y naught also passes through 0 at discrete locations. Okay. So, using these values we can determine what are the values of the coefficients. Okay. So, the function that I had here, the solution, okay, for n is equal to 0, the function f is equal to a times j0 of beta n beta r. Okay. I have the boundary condition that at r star is equal to 0, f is equal to df by dr star is equal to 0. The symmetry condition that the derivative has to be 0. Okay. I have the symmetry condition that at r star is equal to 0, df by dr is equal to 0. Okay. And you can see that the function j0 satisfies this condition. The derivative of this function is in fact 0 at x is equal to 0. Okay. The derivative of y0 does not satisfy this condition. Okay. It has a logarithmic divergence and therefore, the derivative is not 0 at y not equal to 0. You can see that the slope is increasing as 1 over the distance 1 over x as x goes to 0. Okay. So, the only way that this boundary condition can be satisfied is if this coefficient b is set equal to 0. Okay. The only way that this boundary condition is satisfied is if this coefficient b is set equal to 0. The second boundary condition is that at r star is equal to 1, f has to be equal to 0. Okay. At r star is equal to 1, f has to be 0, right. At r star is equal to 1, the function is f has to be equal to 0, which implies that j0 of beta has to be equal to 0. Okay. At r star is equal to 1, if f is equal to 0, that means that j0 of beta has to be equal to 0. That means that beta has to have one of these, okay, discrete values, because it is only at these discrete values that j0 passes through 0, and the boundary condition requires that j0 of beta has to be equal to 0. That means that beta has to be one of these discrete values. Okay. I will call this as beta 1, beta 2, beta 3, etc. Okay. So, beta has to have one of these discrete values in order to satisfy the boundary condition. Okay. Therefore, the function f of r plus is equal to a times j 0 of beta n r star. Okay. Okay. This is r star, where beta n has one of these discrete values. Okay. And therefore, g of t has to be equal to the exponential function that we had derived earlier. Okay. That we had derived earlier, where beta is equal to one of these discrete values beta n, because it is only one of these discrete values that satisfies both boundary conditions. So, g has to be equal to e power minus beta n square T. Okay. And therefore, the total temperature field T star has to be A j 0 of beta n r star times e power minus n square t. Okay. That is the solution that satisfies the spatial boundary conditions as well as the equation. Okay. If you substitute this into the equation, I will get minus beta n square on both sides. Okay. So, it satisfies the equation. It satisfies both spatial boundary conditions. The derivative is equal to 0 at 0, the value is 0 at 1, provided beta n is one of these discrete values. Okay. Provided beta n is one of these discrete values. Okay. Therefore, it is a solution of the equation for any value of n. That means that the most general solution is the summation over all n, okay, of a n times this. Okay, is the summation over all n of a n times this. Okay, so, that is the most general solution. How do we find the coefficients a n? To find the coefficients, we use the orthogonality relation. Okay, to find the coefficients, we have to use the orthogonality relation. Okay. If you recall, in the previous case, okay, so the solution is T star is equal to summation of a. So, let me see, I had used I and j in the previous case. So, I will just use I here, okay, instead of n. Okay, j naught of beta n r e power minus beta n square t. Okay. That is the general solution. The coefficients have to be determined from the condition that at T star is equal to 0, the temperature is equal to 1 for r star less than 1. Okay. Substituting T star is equal to 0 in this, I will get the summation over I a I j naught of, there is an n here, I should use an I here. Okay, I just use the index I to make it consistent with what we had done for Cartesian coordinate system. Sorry, at t equal to 0, this exponential is all equal to 1. So, it appears that we have an infinite number of coefficients and we have only one equation. Okay. However, we can use the orthogonality relation. So, what we do is multiply left and right by j naught of beta j r times r, okay, and integrate. Okay, and integrate from 0 to 1. Okay. So, if I do that, what I will get is that the summation of I is equal to 1 to infinity of a I integral 0 to 1, okay, dr star times r times j naught of beta I r times j naught of beta j r, okay, where both beta I and beta j are solutions of this, okay, are solutions of j naught of beta I is equal to 0. Okay. Both I and j are solutions of this. Okay. So, both I and j are locations where this function passes through 0. Okay. Both I and j have to be locations at where this function passes through 0. Okay. So, multiply by beta j. Okay. So, basically I have a series of functions j naught of beta 1, j naught of beta 2, j naught of beta 3, etc. That is appearing within the summation here, and I multiply by a second function which also passes through 0 and integrate, okay, and my equation becomes integral r dr times j naught of beta j r. Okay. It turns out that this integral also satisfies the orthogonality relation. Okay. It turns out that this integral also satisfies the orthogonality relation, that is integral from 0 to 1 r dr, okay, j naught of beta I r j naught of beta j r, okay, is equal to half times j 1 of beta j the whole square for I is equal to j is equal to 0 when I is not equal to j. Okay. Okay. This satisfies an orthogonality relation when it is multiplied by r dr and integrated. Okay. If you recall, when we did it for a Cartesian coordinate system, the cos function, it satisfied the orthogonality when we multiplied by dx and integrated. Okay. When we multiplied two different cos functions and integrated, we got it proportional to the delta function. Okay. So, this can alternatively be written as this is equal to half j 1 of beta j the whole square times delta I j, where delta I j, the Kronecker delta, is equal to 1 if I is equal to j and it is equal to 0 otherwise if I is not equal to j. Okay. So, on the left side I get summation I is equal to 1 to infinity of a I times half j naught of beta I, sorry, j 1 of beta I the whole square times delta I j. Okay. On the right side, you can do this integral numerically. It turns out that there is an analytical solution as well, and on the right side the analytical solution is j 1 of beta j divided by beta j. Okay. That is the analytical solution on the right side. Okay. Okay. On the left side, the series, all terms are 0 unless I is equal to j. Okay. Therefore, I will get a j times half j 1 of beta j the whole square, okay, is equal to j 1 of beta j by beta j, which implies that a j is equal to 2 by that is the final solution. Okay. And therefore, in the equation my final solution T star is equal to summation I is equal to 1 to infinity of 2 by beta I j 1 of beta I, okay, into j naught of beta I r star e power that is the final series solution for the temperature profile in this cylinder. In the next lecture, I will briefly review the solution procedure that I had used, and I will say a little bit about why this orthogonality relation follows from the differential equation. So, I will continue this in the next lecture. I will see you then.